I thought I'd make a video just quick to go through the solutions for that review Jamboard from the Unit 4 chapter review. So the first one, multiple choice, it asked for f prime at 1. So if we take the derivative of 7x is 7, derivative of negative 3 is 0, so I didn't even write it, and derivative of ln x is 1 over x. Then subbing in x equals 1, we get a value of 8, so that answer is E. For this one, we have a function here that we've got, this function looks like a quadratic over linear, but because these guys cancel out, the x minus 2's, we're left with a hole at x equal 2, so it'll look kind of like the line y equals 2x plus 1, but just with this hole there. So we're going to find what y value would be there if there wasn't a hole, and that would be the y value of 5. And then we're going to put that in for the k to make that kind of fill that hole and make it not discontinuous. Now this one is kind of interesting, and the important thing to recognize here is that this limit, so if you're looking at the limit of ln of 4 plus h minus ln 4 over h, that really is the definition of the derivative at x equals 4. So what we're really looking for is what's f prime at 4 if the original function was ln x. Now the derivative of ln x is 1 over x, and then just putting in that 4 we get 1/4. And I have a couple more examples at the end of similar questions. Here, this is kind of an example of working backwards. So we are given the derivative here, and we want to see what function would we have started with to get a derivative of that. And I'm going to kind of erase this out because I had the answers up here. But just to kind of talk through this, we would have, we know that what function would it be if the derivative was cos? So we know that the derivative of sine is cos, so that this is going to have something like that, sine of something. Now I know when I take the derivative of sine, I don't change the angle. So whatever angle I ended up with in my derivative, that would have been the starting angle there. So that'll be sine of 2x. Now off to the side, if I just had sine 2x, the derivative of this, y prime, would be cos 2x, but then multiplied by 2. Now, that's not what I have for my derivative. I have just cos 2x. I don't want that 2 out front, so I'm going to have to put something here in the original function that will cancel out with that 2. So I'm going to put a 1/2 in front. So then the derivative of 1/2 sine 2x would be 1/2 cos 2x times 2, like I did over here, and then the times 2 and the 1/2 coefficient would cancel out and give us what we were looking for. There is a plus c in the answer at the end because it could have had any number added on because the derivative of a constant is 0. You don't need to include that because it just could be a 0 to start. So for this one, hopefully you guys can identify that here we're looking at the rate of change of the function when t equals 5 is 2. So we're looking for a rate of change of 2 at a time of 5, and that's D. The temperature of the room is increasing at a rate, so that's IRC, of 2 degrees per minute, 5 minutes after it was adjusted. Most of the other ones, we're looking at ARC. So this is 2 degrees over the first 5 minutes. So that is an interval, not an instantaneous. So that's an average rate of change, as is this constant rate per minute. That would be average rate of change. This one in A, it just said the temperature of the room is 2 degrees. That's not the temperature because H prime is the rate of change. So taking a look at the limits here, which one of these is false? Basically kind of a whole bunch of limits, like do they exist? So the first one, the limit as x approaches 2. And you can see I've got red arrows here. This is what's the value of the function as we get close to x equals 2 from both sides. So right around there, the value of the function gets close to a y value of 2. It's not equal to 2 because we have that point down there, but that's okay. The limit does exist. For b, it says the limit of f at x as x approaches 3. So kind of similarly, I've drawn these blue arrows in here. It's getting close to a value of 5. That limit exists. C says the limit as x approaches 4. So here, if we approach 4 from the left, we come down towards 2, and if we approach from the right, we're coming up to 4. So that limit will not exist because the two-sided limits are not equal. The last one at 5, no, that would not be false because that limit would just equal 6. And is the function continuous at 3? Remember, continuous just means can I trace it without lifting my pen or pencil? And yes, I can. Here we've got a graph shown in our original function. Now, if we take a look at this function, remember that where the tangent lines are horizontal, like there and there and there, that would mean the derivative would equal 0. So there and a little bit over there and there. And then where the function is increasing, for instance, between a and that maximum point, the value of the derivative is positive. So it's going to be small positive, bigger positive, smaller positive. So small positive, bigger positive, smaller positive. And again, we don't know the scale. That could go like this. I don't know. It doesn't matter as long as it's going into the positives and then back down towards the 0. And where the original function's decreasing, the derivative will be negative. Again, small negative, bigger negative, smaller negative. So that would be A for our answer. Here, find the value of the following. So the limit as x approaches -3 of g at x. So here we're going towards -3 from both sides. From the left and from the right, we are approaching the same value. Those would both be -3. For b, the limit as x approaches 6. So for here, we can approach 6. Oh, sure, it's going towards -5, but what about the other side? So the limit as x approaches 6 from the right, oh, not f at x, that's g at x, does not exist. So if both sided limits don't exist, then you don't have a limit. And the limit as we approach 2 from above, from the right, would be there, going towards 3. And then the last one's kind of interesting. What's the derivative of the function at x equals 1? Remember that the derivative is the slope of the tangent. So around that point, it's a linear function. What's the slope of that line? The slope of that line is 1. So for D, slope of the tangent. I will go through and match these ones up and post this in the link. But that may get a little bit messy, so I'm going to do that after the video. And these were the ones you guys were working on independently. If you want me to check any of those, just let me know. Now here, I want to take a look at, can we graph the derivative of this function? This is from the previous slide, that one where we were doing the limits. And I've colored in, I don't want to consider these kind of weird points that are out there, but let's just graph this function and think about what we know about the derivative of the function. So first of all, I know that where I have a horizontal tangent, where it's a turning point, the derivative is 0. So there and there. Maximums and minimums have a derivative of 0. Now here, in this first section, between -5 and -3, my function is decreasing. So that means my derivative is negative. So here I have a negative derivative, and it goes from pretty big negatives to much smaller negatives. So I'm going to go somewhere from big negatives to small negatives. Doesn't really matter. And then here my function is increasing, and it starts increasing a little bit, and then it's increasing some more up till 2. So I'm going to just continue this right through and put an open circle. I'm putting an open circle because we can't take the derivative at that corner part. We don't know what the rate of change would be in there. Okay. The next segment of this graph is between -2 and 0. And in that section of the graph, the slope is 0. So here, I'm going to again open circle because I don't know what's happening on those weird endpoints. But this would be the derivative is 0. So it's right flat at the x-axis. The next segment here, I have that this would be a slope of 1. So it's a constant slope, but it's at 1. So I'm going to go across there. And then the last piece, from 2 till 3, it's got a positive slope, but it's getting smaller. It's bigger there than it is there. So a positive slope getting smaller, and I don't know where this line would start. It could start up there and be kind of a line segment like steeper, or it could start there and be not so steep. That part doesn't matter. It should just start in the positives and go down. And here, for the last segment from 3 till 6, this is going to be decreasing, and it starts off small negatives and gets bigger and bigger negatives. So it's going to go somewhere in like that. Doesn't really matter where it ends up. The last thing is 2 more examples that I put up that were similar to that previous example where it was the limit that really looks like the first principles definition of a derivative. So what this first one is asking us, this is the first principles definition of a derivative if f at x is x to the 10. So this is the parent function, is x to the 10 there. So what we're looking for is f prime at 2. So we're looking for f prime at 2 if f at x is x to the 10. So that's what we want to find. So if f at x is x to the 10, f prime at x is 10x to the exponent 9. And then f prime at 2 is 10 times 2 to the 9. And you could do that on a calculator. I don't have one handy though. Okay. The next one, our parent function here is sine x. So we know f at x is sine x. And what are we looking for? We're looking for the derivative of sine x where x is pi over 2. So we're looking for f prime at pi over 2 if f at x equals sine x. And that's not such a hard question because then we can find the derivative, which we know is cos x, and just sub in pi over 2. Which is 0. So if you guys have any other questions, please add them to the regular homework Jamboard. I will take a look at that tonight, kind of in gaps between parent-teacher interviews. Try to put as much detail if you have questions as you can so that I can provide good written answers, because I probably won't have big enough gaps between my interviews at parent-teacher interviews tonight to do full video solutions.